Thanks. This is a joint presentation of some work done collectively by Alcatel, Cisco, and Juniper. And the history of this work starts at a NANOG in Washington about 2 years ago. There was a security BOF, and someone had mentioned that they would MD5 authenticate their BGP peering sessions if there was a way to update keys without bouncing the BGP session. Well, I remembered that comment. Later on, there was another NANOG, I think in Seattle, where we talked about how many people were actually MD5 authenticating BGP, and a surprisingly small number of people were actually authenticating. Well, out of that work, another customer reminded us that we needed something better as far as authenticating BGP peering, and for that matter, all TCP-based routing protocols. So this work came out of this. Here the motivation we've already talked about. Not enough operators are MD5 authenticating. Current practice, RFC 2385, doesn't fulfill operator requirements. And basically there are a couple of reasons why they aren't using it. One is CPU utilization. I apologize for the first bullet there. I did these slides before. It's a joint presentation. It's not so much an issue for Juniper or Cisco or Alcatel because forwarding and control processors are separated. So CPU utilization isn't so much an issue. Key management is an issue. There's no way to refresh the MD5 key without bouncing the BGP session currently. And the other thing that's an issue is the cryptography is weak. There are many well-known attacks on MD5. So we knew we needed to come up with something better than RFC 2385. The question is, what would it be? Would we do something in the application, in the transport layer, or in the network? We could have done it in the protocols, done some kind of authentication in BGP, something in LDP, something in MSTP. In fact, BGP used to have an authentication mechanism inside of it. That was recently deprecated because no one used it. We could have used TLS, again, authenticating at the application layer, and we decided against that because although it would authenticate the BGP payload, it would authenticate the BGP, the TCP payload, it wouldn't authenticate the TCP control information. So we would still be vulnerable to things like blind insertion attacks where the reset bit is set. So we decided not to authenticate at the application layer. Our two choices were to do it at the transport layer with yet another TCP option, or to do it with IPsec. And we decided to go the transport layer route, and we'll talk about why in a little bit. But before we talk about why we made that decision, let's talk about the solution we came up with. The solution is characterized by a TCP authentication option. The option has in it a message authentication code and a number. The number identifies one of many keys that could have been used to generate the MAC. Now, where do these many keys come from? On both systems, the sending and receiving system, we manually configure a keychain. A keychain is a list of keys. The sending system decides which key to use based on time. It generates the MAC, it generates the TCP option that has the MAC and the key identifier in it, sends it to the receiving system. It has the same keychain, looks for the appropriate key, does the lookup. Another characteristic is we can use some stronger cryptography. Rather than using MD5 to authenticate, we can use HMAC SHA-196, CMAC AES 12896. For that matter, we can use any authentication algorithm, but these are the two that are most recommended. This is a look at the new TCP option. Like any TCP option, it starts with a kind and a length. The T and K bits we'll talk about in a little bit. The algorithm ID tells you what algorithm we use to generate the MAC. The key ID tells you which key off the keychain we use to generate the MAC. So, a look at the keychain. Keychain contains up to 64 keys. Each key has an identifier, an authentication algorithm, a shared secret, and a start time and an end time. Actually, to be more accurate, it has a start time and an end time, both for receiving and transmitting, and those don't have to be the same. Typically, the end time for receiving will specify a wider window than the end time for transmitting, and that way we deal with clock skew when the sending and receiving systems have their clocks set a little differently. So, let's take a closer look at how the authentication scheme works. The sending system's first job, he has a TCP segment he wants to send out. First thing he has to do is identify the active key on its keychain. It does that based on time. Okay. A little closer to the mic. Okay. It identifies the active key based on time. Basically, it's looking for a key whose start time is less than the current time and end time greater than the current time. If there are no candidate keys at all, the sending system discards the outbound packet. If there are multiple candidates, it selects the key with the most recent start time for sending. Having selected the active key, it calculates a MAC. It calculates the MAC over the TCP pseudo header, TCP header, and TCP payload, and by default it includes the TCP options, except of course for the option that it's calculating. Then it assumes that the MAC is 0. Going back to the T-bit, it's possible that you don't want to include the options because you have some middle box in the line. If you set the T-bit, that means that the options are not included. Anyhow, the sending system formats the enhanced authentication option and sends it out. Now the receiving system gets it. First thing it does is look at the key identifier on the option, make sure it has that key. If it doesn't, it throws the packet away. Next thing it does is make sure that the key is not expired. If it's expired, it throws it away. If it has the key and it's not expired, it calculates the MAC. If the MAC it calculates is equal to the MAC it's received, then it accepts the packet. Otherwise, it declares an authentication error. In the case of an authentication error, the receiving system discards the datagram, logs, and it doesn't send any indicator to the originator. That's very important. Also, it doesn't play with any of the counters in TCP if the packet does not pass authentication. Okay, here we have a couple configuration examples, one from Juniper, another from Alcatel, and we have another from Cisco, but unfortunately I don't have it on this slide deck, so we'll update the slide deck before it's posted to the web page. In any event, that's the presentation. Before I open the floor to questions, I'd like to ask a couple questions of the audience. How many of you are authenticating IBGP sessions now? And how many are not? Oh, so the majority are actually authenticating now. How many of you are interested in a better way to update keys? Okay, about the same crew. Okay, open the floor to questions now. None at all? Thanks.
Got one. Russ Mundy. Are you planning on taking this work into the IETF so it gets published through that process?
Yes, it's already been introduced to the TCPM working group. was presented at RPSAC and SAG-2. We're waiting for some feedback to see if we can progress the work any further. But also appreciate any support you could give us on the SAG working group mailing list.
Okay, thanks.
Randy Bush, IIJ. Hi, Ron. Were there any simpler proposals?
There were
Clearly,
no
this was designed for the IVTF.
There were no alternative proposals other than the ones that we put up in the first slide and rejected ourselves.
This seems pretty meaty.
Steve Bellevin, Columbia University. No longer security AD at the IETF. Two things. One, and I know the questions come up on the SAG list. Could you tell me more about why you're rejecting ICE and IPsec, since that does all this? Admittedly, it does far more, which isn't good, but it does what you're asking for. Two, why not tie the algorithm to the key and get it out of the header and give you more bits for ID over something else?
Okay, I'll answer the first question. The second question first, since it's easier. Actually, the algorithm could be taken out of the key and put in. Well, actually, let me clarify the question. Are you asking why the algorithm is in the TCP option?
That's correct.
Or why it's in the key as opposed to...
Why is it the TCP option instead of associated with the key?
Okay. Actually, that's the kind of comment that we're looking for in the IETF. We argued both ways, whether it should be in the option or not, and I'm kind of up in the air as to whether it wants to be or not. One argument for putting it there is it's a very quick way to check without actually calculating a MAC, so you can throw away some attack packets before you've actually calculated a MAC. But personally, I'm not married to that idea. The second question is actually the more interesting one. Why not use IKE? And here you're talking about IKE with just authentication?
Of course, there's no need. There certainly doesn't. I don't perceive the need for confidentiality here. I doubt that most other people do.
Agreed. There's probably no need for confidentiality. We talked about that, and there were a couple possibilities. One is to just use IPsec with pre-shared keys, but then you have the same problem of having to roll over the keys. You'd need some way to either negotiate keys. Once you've done that, you need some way to authenticate. As it turns out, those are all probably good ideas. What we would like to do is do this in a first phase, to have just a way to do manual key rollovers. In a second phase, people will talk about things like how you'll negotiate a key for one-time use.
Doesn't really answer my question with IPsec already including pre-shared key mode for IKE to IKE will negotiate a key and authenticate it. At least you get a separate session key.
Okay, if you needed pre-shared, if you were to use pre-shared key mode for IKE, you'd need something like this to roll over the pre-shared key in the first place, because there are many people with access to the router. This is a large topic that's probably about to brew on the SAG mailing list. There was some activity on it this weekend.
Thanks.
I'm Chris Rash. It's not a question. Two completely different opinions there. I think you made the right choices, and thank you.
Thanks.
Barry Green, Francisco. To answer Steve's question, and maybe over to Randy's question, why is this a little bit more complicated? It's because of the being able to have multiple keys and roll it over. I mean, you know, we've had MD5 out there for years, and I know some of you guys with networks out there who've had their keys, the same key, for like 10 years. Because you can't change them out without dropping off sessions. So I think one of the dominant themes is to have a way where you can have, you know, OC 768 sessions and have a hitless rollover of a key, which IKE didn't allow that. I mean, in looking into it, we couldn't find a way where we can get that done with IKE. So this is going to be from the IETF, because this originally started with the question, is this going to be into the IETF? I think the question is, this isn't the way that people have been thinking about doing IETF. This is very much an operator-driven sort of requirement, which is having that hitless rollover of the key.
Thanks.
Jared Mach, NTT America.
Jared?
Hi. So I'm just going to ask my question in public. You already know it. So how do I go and take my internal IBGP session and roll the key from existing MD5 infrastructure to this without making the NANOG mailing list?
Okay. We need a solution to that problem, and look forward to version 5 of the draft.
Ron?
Yes.
Bora Akil from Broadcom. The comment about Ike being able to not roll over keys without a hit is kind of incorrect. If you did Ike v1, that the IPsec assays that you would use are not coupled to the Ike assay. So, in fact, you can lose your Ike assays, have your IPsec assay, rekey your Ike assay, and then in the meantime reestablish your IPsec session. So this is with Ike v1. Ike v2, unfortunately, couple these together, but I don't quite understand in this environment where we're so hung up on pre-shared keys. Because just like you're exchanging keys across, if you were exchanging certificates between two service providers or within the same service provider, which to me is a non-issue, then Ike should be able to suffice, because with Ike, every time you do have a new session, you regenerate the keys. So maybe I'll participate in the mailing list and kind of discuss this further there. I agree with Steve's comment here that you're basically doing a lot of the stuff that Ike and IPsec does all over again. Nothing wrong with that. It's just that maybe we should try to reuse some of what we have.
Okay. Barry?
So so in changing the keys, you got to think of it this way. And a lot of you who run networks and have managed MD5, you know this. So what you want to prevent is a colo meet, because colo meets are a pain in the butt. So I want to set my key. Here's my new key. My old key's working. Here's my new key. I send an email message over to Jared and say, hey, Jared, I'm resetting my keys. And Jared's not even going to look at it, oh, it's Barry's email. I'll look at it next week. And I finally look at it and says, okay, I'll go ahead and set the key. Here's the new key. And it rolls over. And there's no hit. And nobody knows about it. So you got to look at not only how do you roll over keys on like OC768 where you can't afford a half a second, otherwise the customer see it. And you also got to realize how people operate their networks and work with it in a system that works how they work, and everybody's squeezed for time and things like that. So that's where some of the constraints we're running into with this, and why this is shaping out to be different. So we encourage people to participate. I think SAG is the IETF forum where this is being conversed about right now, and if you're not on there, that's a good place to join up, at least for this time period of this discussion.
Looks like it. Thank you very much.